Let's start with topic 4. This one is asked so many times across papers. Paper 3, 4, 5, 10 as question 9 short question. Okay, so topic 4 is Cayley-Hamilton theorem. So step 1, quick recap. What's a characteristic equation? You saw this in topic 2. For any square matrix A, we form this equation. When you expand this determinant, you get a polynomial equation in lambda. For example, degree 2 degree equation in lambda, and 3 degree for 3 by 3 matrix. For 2 by 2, it's 2 degrees. This polynomial equation is called the characteristic equation of matrix A. Now step 2, what does the Cayley-Hamilton theorem actually say in plain English? First, here is the idea in super simple words. If you take the characteristic equation of a matrix and everywhere you see lambda, you replace it with the matrix A itself, and everywhere you see a plain number or constant, you replace it with that number times the identity matrix. Then the whole equation becomes true. It becomes the zero matrix. So basically every square matrix satisfies its own characteristic equation. That's the whole theorem. It sounds fancy, but it's really just plug the matrix into its own equation and it works out to be zero. Step 3, the formal statement. Memorize this, literally copy this in exam for state Cayley-Hamilton theorem. So Cayley-Hamilton theorem says every square matrix satisfies its own characteristic equation. That's generally the full statement for state questions. 2 marks, 1 sentence. Some people want a tiny bit more detail, so here is a slightly fuller version you can also use. So if this is characteristic equation of a square matrix A, i.e. this is the characteristic equation after opening it up, because it's in lambda, right? So lambda raised to the power n. Why doesn't it have any coefficient? Anyways, up to the last coefficient. This is weird, like I don't like this. So basically lambda is replaced with a, then this is equal to 0, the zero matrix. Anyway, so let's see this in action with tiny concrete 2 by 2 examples, so it's not just abstract words. Let's take a matrix 1 2 3 4. Find the characteristic equation. So if we take this matrix, subtract lambda I, we get this. We just subtract lambda from each diagonal entry, nothing else changes. Take the determinant, set to 0. Now using the 2 by 2 determinant rule, top left times bottom right minus top right times bottom left, we calculate determinant. Expand this carefully term by term. Use FOIL. First outer, inner, last what? First 1 times 4, then 1 times minus lambda. Yeah, minus lambda times 4 and minus lambda times minus lambda. Adding these, we have our equation. So our equation is this is the characteristic equation. Now apply Cayley-Hamilton theorems. Now replace lambda with a and the plain constant with the constant times I. The theorem says this matrix equation must be true. Since lambda square equals is a square, and this is how they replaced. Anyways, and it all equal to 0 matrix, not the number 0. So these are all matrices and this is 0 matrix. Step E, let's verify it's actually true. This is the verify Cayley-Hamilton theorem type question you will see. So first calculate a square. Simply when we multiply two matrices, we multiply row 1 with column 1. So 1 2 and 1 3 1 3. Row 1 with column 1, row 1 with column 2, then row 2 with column 1 and row 2 with column 2. As you can see, to get our new matrix, I'd completely forgotten this multiplication of matrices. Okay, so now calculate. Now calculate 5a, simply multiply 5 with all the elements. Now calculate 2i, 2 multiply with identity matrix. Now put it together. Now this is simple, 7 minus 5 minus 2, 0. You can see the calculation. It is simple, so it comes out to be 0 matrix. This was the code for zero matrix. It didn't work out, but it works. The matrix satisfies its own characteristic equation exactly as the theorem claims. So step 5, why do we even care? So do we not have to like prove the theorem or anything? So we state the Cayley-Hamilton theorem's definition and then we verify it using real examples. Why do we even care the practical use bonus, since it also shows up as long question? Okay, so Cayley-Hamilton isn't just a party trick, it's used to find A inverse without the painful adjoint method. Since you have question 1, question 2 type long question asking verify Cayley-Hamilton and compute A inverse, here's the shortcut logic just so you recognize it later. We don't need to master this today. So okay, so from this equation rearrange to isolate I, uh, find divide by 2, then factor out A. This mean that A inverse, oh, A inverse is just equal to this. You get the inverse using only A itself. So no cofactors needed. We'll fully practice this when we hit the long question, but it was simple. Okay, so master summary for exams. First, state Cayley-Hamilton theorem. Just write every square matrix satisfies its own characteristic equation. And for state and proof, bigger long version, we'll cover the proof later when doing long questions, since question 9 only ever asks to state it, not prove it. Okay, so just the statement above is what question 9 wants. Don't waste time on the proof for short question prep. Rule number, okay, fine, so this topic is complete, at least for the short questions.